Hey everybody, it's Mr. Brew from Infinity the Math Institute with lesson 2A of our ongoing series of Introduction to Higher Level Mathematics. The reason I say 2A is because we're going to break this lesson up into two different classes. And today we're mostly going to be talking about an introduction to integers and the coordinate plane. All right? We're going to be talking about integers which are simply positive and negative numbers. No fractions, nothing like that, just whole numbers and their opposite, which was a vocabulary word from last week. Integers are whole numbers and their opposite. So it goes all the way from negative infinity to -2, -1, 0, 1, 2, 3, and all the way back up to infinity. Those are your integers. And you have to be comfortable using them. You have to be comfortable labeling things. I mean, a lot of people seem to understand, like for example, temperature. It could be below 0 degrees. We'd say it's -3 degrees or -10 degrees or 10 degrees below 0. They all have that same connotation of being less than 0. And getting comfortable with these numbers or integers that are below 0 is going to be really important as we progress on our journey towards higher level mathematics. We're going to be talking about operations. How do we add, subtract, multiply, and divide with these integers, including negative numbers? What is -4 minus -7? Well, by the end of this class, you'll be able to answer that very, very easily. We're also going to be talking about order of operations, which is super important. And don't let me catch any of you saying PEMDAS, because PEMDAS is very misleading. And we'll explain why as we get through that portion of the lesson. We're going to be talking about absolute value, which is technically just the distance from 0. And distance is always a positive. I mean, if Wendy's is a mile that way, you would never say Wendy's is -1 mile that way, right? So distance is always positive, absolute value is always positive. We're going to be talking about inequalities, all right? Greater than or less than, which you're going to see in all kinds of connotation on the news, at amusement parks, everything else, but we'll get into that a lot more. And we're going to be talking about the coordinate plane, which is really important. It's used to find location. We're going to talk about the origins of the coordinate plane, all right? We're also going to be checking your homework. We're going to have a quiz on the things that you were supposed to know from last week. And we're going to review a couple of your homework problems before getting into it. So are you ready? Let's get started. All right, so let's start with a quick review of what we talked about last week. Last week we were talking mostly about the fundamental theorem of arithmetic, which you need to know is that every single number, whole number greater than 1, is a unique product of primes. And we talked about that. We also talked about how to get the GCF and the LCM. You need to know, what is the GCF? I know it's the greatest common factor. What does that mean? Yes, the biggest number that divides into two other numbers. And the LCM, and don't tell me it's the least common multiple, I know that. What's the LCM? The biggest number that two numbers can divide into. Very, very good. All right, we also talked about stuff like subtraction is adding the opposite, which is going to come really in handy today. We talked about how division is multiplying by the reciprocal. 8 divided by 2 is the same thing as 8 divided by 1/2. What's the definition of a prime number? A whole number greater than 1 whose only factors are 1 in itself. You need to know the first 10 primes. You should pause it and recite the first 10 primes. And you should have said 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Very, very good. And you should be able to start recognizing when numbers are prime. Later on in these lessons, we're going to talk about divisibility rules so you could check your work. But as of now, you should have a feeling of whether something's prime or not. You got to know that 45 is not prime because it ends in a 5. It's divisible by 5. Anything that ends in a 0 is divisible by 10. Any even number is divisible by 2. So I love to tell my students, name 2 even prime numbers. And of course, that's a trick question. There's only one even prime number, 2. Every other even number is what? Composite. It's a composite number. Very good. All right, so I'm assuming you all got your papers numbered from 1 through 10 because you know what time it is. It's time to do some squares and cubes. Yes, I still do have a little sympathy because I know it's only our second class, so I didn't make it too hard. It is going to get tougher. So number your paper from 1 to 10, and I will give you 5 seconds to answer each question. Are you ready? 3 cubed, 7 squared, 5 cubed, 9 squared, 2 cubed, 12 squared, 4 cubed, 14 squared, 1 cubed, 10 squared. Pencils down. And check your work. You should be getting a 9 or a 10 on all of these, preferably a 10. I'm just letting you say 9 in case you made a silly mistake. The answers are 27, 49, 125, 81, 8, 144, 64, 196, 1, and 100. Now, you should have your squares up to 15 memorized and your cubes up to 10 memorized, all right? I'm not going to increase that just yet. We're going to do another week with just those numbers, and then I'm going to throw in a couple more. I promise you, as we continue with these lessons, having these numbers memorized is going to be essential. Also, understanding the vocabulary, word for word, is going to be essential. All right, for example, math is the most important thing in becoming a lawyer. Why? Because we take the definitions or the laws and we apply them to new situations. And to have a real firm concept of the word-for-word definition is just like a good lawyer having a good conceptual understanding word-for-word of the law. All right, so let's get into today's lesson. Are you ready? Get those pens and paper out. All right, and I know I like to beat a dead horse, and I'm sure you've heard me say this multiple times already, and you're going to hear me say it again. Vocabulary is super duper important, and that's why every single one of our classes we're going to have a vocabulary segment. These documents are provided for you in the links in the description, so I encourage you to print them out. But at the same time, please also take notes. Make index cards. If you are to listen to the lesson, write down the notes, and make index cards, it's going to make your life so much easier. You're going to memorize these properties or vocabulary words or whatever the case may be. So let's start out with a number line. All right, a number line is just a line with numbers on it. It's kind of a tough definition, but you got to understand that we're going to be using number lines. All right, places where we see number lines in everyday life, we see them on thermometers. Clocks are a circular number line. I mean, just any kind of a line with numbers, your speedometer, whatever the case may be, is an example of a number line. A lot of you with the old-fashioned thermostats, you're just adjusting the heat using a number line. Inequalities. That's simply saying that you're going to have not equations, but inequalities saying less than or greater than, or less than and equal to and greater than and equal to. We see them everywhere. At the amusement park, you must be at least this tall to ride on the roller coaster. That means you must be greater than or equal to this height. When you're watching the weather, you always want to know what the temperature is going to be. The high temperature today is going to be 70 degrees. That means the temperature will always be less than or equal to 70 degrees. All right, so we deal with inequalities all the time, and we're going to have to use them in our equations as well. It's not a big difference, but you've got to wrap your head around the concept of inequalities. Absolute value, I just told you a little while ago, it's the distance from zero. Very important. Always a positive number. The absolute value of 3 is 3. The absolute value of negative 3 is 3. The absolute value of 0 is 0. The coordinate plane. And this is pretty much the foundation for everything visual in mathematics, from modeling to everything that you could ever think of. The coordinate plane is simply two perpendicular number lines. The horizontal number line is the x-axis. The vertical number line is the y-axis. All right? And they intersect at 0, 0, which is called the origin. Now, anything positive on the x value goes to the right. Anything negative on the x value on the x-axis goes to the left. Anything positive on the y-axis goes up. Anything negative on the y-axis goes down. and you simply use an ordered pair, which is two numbers, parenthesis x, comma, y. The x is your horizontal value, the y is your vertical value. And we could use this system in order to find location or a data point in any situation. All right, it's also known as the Cartesian plane. And why is that? Well, there was a French mathematician named René Descartes. Now, this was about, don't quote me on this, but I'm pretty sure it was about 400 years ago. And he was not feeling well. He was laying sick in bed, and he was FaceTiming with his friends on his iPhone, and he wasn't able to, they didn't have the camera flip back then. They could only see each other's face. So it was very hard for him to show his friends around the room with his cell phone. So he had a fly going around on the ceiling, and he was trying to explain or quantify where the fly was landing. And saying 3 feet up, 12 feet to the right, or 7 feet in from the diagonal at a 45-degree angle, it wasn't working at all. So he said, what if I constructed two imaginary number lines perpendicular to each other, and if it's up and to the right, it's going to be positive x, positive y. If it's left and up, it's going to be negative x and positive y, and so on and so forth. And he created a grid on his ceiling. And then every time, now that he had this grid, every time the fly landed somewhere, he was able to just shout out two numbers, and everybody knew exactly what he was talking about. And again, that's all math is simplifying a way of counting or quantifying something. And René Descartes invented the Cartesian plane, which we still use today. Every time you see a graph, no matter what it's talking about, it's usually modeled after the Cartesian plane. So places you see the Cartesian plane in real life, like I just said, every modeling equation that you see on the news and stuff like that is an example of the Cartesian plane. Sometimes you only see the top right of it, the positive and the positive, but other times you use the negatives. Also maps with their grids. I know we all have cell phones now and we don't use maps as much as we used to, but even your cell phone map app is using a Cartesian plane to find coordinates and to locate things. Ordered pairs, like I told you about, it's parenthesis x, comma, y, parenthesis, which is simply giving you the horizontal value and the vertical value. It's a lot easier to understand when you visualize it, and I'll show you that in just a moment. Graphing. Graphing, when related to the Cartesian plane, is understood, but graphing in general is just a visual representation of math, all right? You could have a pie graph, a bar graph, a line graph, a Cartesian plane with data points, modeling mathematical equations. Graphing is just a visual representation of math. Perimeter, distance around something. Obviously a circle has a circumference, but we'll talk about that later. The perimeter is simply the distance around something. Fencing, you got to measure the perimeter of your property to put up a fence. Polarity. Anytime we discuss polarity, it's simply discussing positive or negative numbers. What's the polarity of the number 5? Positive. What's the polarity of -1? Negative. So when I say polarity, I'm referring to positive and negative. Opposite refers to polarity. So what's the opposite of 3? -3. What's the opposite of negative pi? Pi. The opposite is just changing the polarity of a number. Whereas the absolute value is changing the polarity of that number to a positive. If it's positive, it stays positive. If it's negative, it turns into a positive. The x-axis is that horizontal axis where y equals 0. Above the x-axis, y is positive. Below the x-axis, y is negative. On the x-axis, y is always equal to 0, while there's a whole bunch of different x values. The y-axis is the vertical number line. Now, when x is positive, I'm trying to reverse it. X is positive, it's over here of the y-axis. When x is negative, it's to the right of the y-axis. When x is 0, you are on the y-axis. All right, so you might want to jot this down on your index cards. We're going to go over this in detail. Adding integers of the same polarity, you add and keep the polarity. 3 plus 3 is 6. -3 plus -3 is -6. Adding integers of different polarity. You subtract the two numbers and then keep the polarity of the highest absolute value. 7 plus -4, 7 minus 4 is 3. The absolute value of 7 is greater than the absolute value of -4, so it's positive. 7 plus -4 is 3. -7 plus 4 is -3, because 7 minus 4 is still 3, but we use the absolute value of the -7. We'll talk about that on the board in a second. Subtraction, just a review from last week, we're simply adding the opposite. 7 minus 4 is the same thing as 7 plus -4. It's got a lot of other helpful hints though from that. Multiplying and dividing, very simple. If you're multiplying and the signs are the same, it's positive. If you're multiplying the signs are different, it's negative. And the same goes for division, because division is a form of multiplication. Again, a review from last week, division is multiplying by the reciprocal. All right, a couple other quick ones. Identity is an operation that does not change the value of a number. And inverse is the way to get that number back to the identity. Make those index cards. We're going to go over each and every one of them in detail, starting now. All right, so the first thing, which may seem like common sense to some of you and others, it might be a little more difficult to understand, is the labeling of integers. All right, number one, north is going to be positive. South is going to be negative. East is going to be positive. West is going to be negative. All right, it's just the way it is. Below sea level, negative. The height of a mountain is going to be positive. You're talking about a withdrawal, it'll be negative. A deposit would be positive. I mean, a gain is positive, a loss is negative, all right? Are we all on the same page with that? I gave you a few problems just so you can make sure you're cool with that. The number line we were talking about, right? Everything to the right of the number line is going to be positive. Everything to the left of the zero, is going to be negative. So -1 is going to be less than +5. All right? But -8 is still less than 5. All right? So I just want to make sure you guys understand how we're going to use the number line and how you can visualize some of these inequalities or deciding which integer may or may not be greater than one another. All right, remember an integer is just a whole number and its opposite. It does not include fractions or decimals and stuff like that. A quick review. I don't know how you like to do it. I think of pointing to the lower number. -8 is less than 5. Some of the kids, they like to think of Pac-Man eating the bigger number. I think of it as pointing to the lower number. Either way, you got to understand that this is red. -8 is less than 5, or -8 is less than or equal to 5. Either one of those would be true. At the same token, 5 is greater than -8, or 5 is greater than or equal to -8. All right? Just remember, if it's pointing to the left, it's a less than sign. If it's pointing to the right, it's a greater than sign. And one of the great things about all these notations and shortcuts that I'm going to be showing you is that math is the universal language. All right? They use these same symbols in China, India, and Russia. All right? So they may not understand your words, -8 is less than 5, but they will understand your mathematical notation, just as you do. All right. Then, if we get into some simple absolute value problems, all right? I talked a little bit about it during the vocabulary intro. This is the absolute value of x. This is the notation. You'll see it in other circumstances, like when you're talking about magnitude and vectors and stuff like that. It's a little bit ahead of us right now, but every time that just simply means the distance from 0 or the distance. This is where x equals x, or x equals -x. Because if the absolute value of -x equals x. So it doesn't matter which one this is. That's a little abstract. In more concrete terms, it simply says that the absolute value of 2 equals 2. The absolute value of negative 3 equals 3. The absolute value of 0 equals 0. All right, we will always have a positive number except for the case of 0, which it would be 0. If you were to have a simple equation, for example, we want to know the absolute value of 2 minus the absolute value of negative 1. All right, the first thing you would do is you would take care of the absolute value signs. What is the absolute value of 2? It's 2. Minus, what's the absolute value of negative 1? 1. And, of course, 2 minus 1 is 1, but what I want you to see it as 2 plus negative 1 is equal to 1. Now when I tell you to do this, I don't want to change your whole thinking or approach to subtraction. I'm just saying when you're doing it in an algebraic sense, understand exactly what it is, because when you get into more difficult problems, that could clear a lot of things up for you. All right, let's get on to graphing ordered pairs. All right, we talked about it a little bit. I just want to expand upon that visually. First of all, I'm going to draw a Cartesian graph. All right, the first thing you need to know is that, this is the x-axis, and this is the y-axis. X is positive, x is negative, y is positive, y is negative. Where they're both positive, this is quadrant 1. All right? And that is where x and y, it's always going to be x comma y. Positive, positive. All right? And then every time we're doing something in math from now on, unless they specifically say clockwise, you're always going to default to counterclockwise. Meaning this is quadrant 2, quadrant 3, quadrant 4. And this is where x is negative, y is positive. X is negative, y is negative. And x is positive, y is negative. Okay? And just some food for thought. If you have a point on an axis, it is not technically in a quadrant. So if it's here, it's 1, 2, 3, 4. On the lines, not necessarily in a quadrant. So if they ask you what quadrant the point 0, 5 is, that is not in a quadrant. So I would say not applicable. But back to graphing the ordered pairs specifically. Now I don't have these all labeled, but I can throw some in there. How about 1, 2, 3, 4? 2, 3, 4. Negative 1, negative 2, negative 3, negative 4, negative 1, negative 2, negative 3, negative 4. All right? If we have the point 3, 1, that means right 3, positive 3, 1, 2, 3, and then up 1, positive 1. That is 3, 1. If we had the point 3, negative 4, it would be 3 positive, 1, 2, 3, 4 negative, 1, 2, 3, 4. That would be the point 3, negative 4. All right, just one more. I'm guessing you understand this by now. But if we had the point negative 2, negative 3, sorry, I couldn't think of a number. Negative 2 is the x-axis, 1, 2. Negative 3 is the y-axis, down 3. And right there is your point, negative 2, negative 3. All right, obviously you need to be able to do it backwards. If I had a point right here, I should see that it's left 3, which gives me a negative 3, and up 3, which is a positive 3. X, Y. Left, up, quadrant, 2, yada, yada, yada. And that's as easy as it is. All right, so I've included a couple of problems for you to not only graph the ordered pairs, but to determine what the ordered pair of a given point would be. We talked about absolute value, talked about graphing ordered pairs. So now, the meat and potatoes, the thing that you're going to use most in the future, is integer operations. Now I'm going to give you 3 different ways to look at integer operations. Alright? The first way is going to be the way that you're not going to use it, but I would like you to consider it when you're thinking about these problems. So let's take a number line. Call this 0, 2, 4, negative 2, negative 4, right? All right, so say we have a problem like 1 plus 2. 1 plus 2. So you start at 1, and then we're going to go positive 2 units, which gives us positive 3. Cool? Let's take a look at another example. Say we have negative 1 plus 3. So you would simply start at negative 1 and go to the right 3. And you would get 2. Simple enough. What if we had 3 minus 4? Very simple. We start at the 3. Now we're going to go left 4. And we end up at negative 1. And then when we get really crazy, say we have 2 minus 4 minus negative 3. All right? So what do? We start at the 2. We're going to go left 4. Then we're going to turn to the left. Then we're going to turn to the right. This is 2 turnarounds. All right, and what does that mean? If you make a U-turn and then make another U-turn, you're back where you started. So it's essentially adding the opposite, which is a shortcut I'll teach you later. But we're going to go left, then right, 3. And there we are at 1. 2 minus 4 is negative 2, plus 3 is 1. That's the most complicated way to look at it, but it is the underlying theory of how we're going to get about it. Another thing I like to show my students, before I teach them the easy way to do it, is algebra tiles. If we have 2 plus negative 4, that simply means I have 2 positives and I have 4 negatives. All right, when we have a negative and a positive, like, negative 1 plus 1, it equals 0. Opposites cancel each other out. So, these cancel each other out, and what are we left with? We're left with 2 negative tiles, which means this is equal to negative 2. All right? Take a look at one more example with algebra tiles, but this is simply for your visualization. If we have negative 8 plus negative 4, you're going to have 8 negatives and 4 negatives, giving you a total of 12 negatives. But what if we have negative 8 plus 5? Well, now here's our 8 negatives. And here's our 5 positives. They all cancel out, and what are we left with? 3 negatives, or negative 3. Okay? Another way for you to visualize it. But the bottom line is, and you should have made these index cards earlier, is to understand the rules. Number 1 rule, when adding integers of the same polarity, you add and keep polarity. So the bottom line is, I'm going to teach you the shortcuts. As long as you're able to visualize and understand what I did previously, these shortcuts are going to be great. If not, practice visualizing first and then implement the shortcuts. So the first example is adding integers of the same polarity. You add and keep the polarity. So 4, positive 4, plus 3, positive 3. We add 7 and keep the polarity. Positive, positive is positive 7. On the same token, negative 2 plus negative 9. We add and keep polarity. 2 plus 9 is 11. What was the polarity? Negative. It's that simple. Rule number 2. When adding integers of different polarity, you subtract the numbers and keep the polarity of the highest absolute value. Please learn how to say that verbatim. So, let's get two integers with different polarity. How about 3 plus negative 5? The first thing we do is subtract. 5 minus 3 is 2. Now, which of these numbers has a higher absolute value? Which number is further from 0? Negative 5. So we will keep the polarity in the highest absolute value. 3 plus negative 5 is negative 2. At the same token, negative 3 plus 5 is equal to 5 minus 3 is 2. And the absolute value of positive 5 is greater than the absolute value of negative 3. So we'll leave that as a positive. One little side note, if you're seeing it for the first time, I just put parentheses to ensnare my negative sign so there's no confusion. Always better too many parentheses than not enough. But here I didn't use one, I could have. All right, a couple other examples would be, say, negative 7 plus 4. 7 minus 4 is 3. The absolute value of negative 7 is greater than 4, so it's going to be negative. At the same time, 7 plus negative 4. 7 minus 4 is still 3, but now the absolute value of a positive is greater, so it's positive. And like you should understand, if there's no sign, it's assumed to be positive. We only need a sign for a negative. But if you put a positive sign, it's not wrong. But you'll get out of that habit pretty soon because nobody does it. All right, really quick, subtraction is addition. So we don't need to make up a whole new set of rules, just understand that subtraction is adding the opposite. So back to the original one, 7 minus 4 equals, the first thing you do is you add the opposite. And now you revert back to your addition rules. 7 different signs, different polarities, so we're going to subtract. The absolute value of positive 7 is greater than the absolute value of negative 4, so it's positive. All right? How about 3 minus 12? All right? Subtraction, you simply add the opposite. Positive 3 and negative 12, we subtract because the signs are different and we get 9. The absolute value of negative 12 is greater than the absolute value of 3, so we're going to make it negative. And now, these should be somewhat intrinsic in your thinking, but this is where it gets really useful. When we get into problems like 3 minus negative 12, you'll be a pro at this really quick if you just do the practice and follow the rules. What is subtraction? Adding the opposite. 3 plus 12, 15. How about negative 4 minus negative 17? What is subtraction? It's adding the opposite. Negative 4 plus 17, signs are different. We subtract, we get 13. The absolute value of the positive is greater than the absolute value of the negative, so it's a positive. Subtraction, simply adding the opposite. Finally, multiplying is super easy. Of course, division is just a form of multiplication. And when multiplying and the signs are the same, or the polarity is the same, it's positive. If the polarity is different or the signs are different, it's negative. I mean, I don't know how much easier it could get. 3 times 4 is 12. Positive, positive. Negative 3 times negative 4 is 12. Negative, negative, signs are the same. Notice, I use an X here, because just in case you're in 3rd grade. As we get older, we start using dots, because we don't want to confuse it with the variable X. Great. And then, it gets even better. We start to just use parentheses. We could say negative 3 times 4. All of these are just multiplication problems. Signs are different, so it's negative 12. All right, another way to say it is 3 times negative 4. I can't help but use the parentheses when I have a negative. And that's also negative 12. Signs are the same, positive. Signs are different, negative. Same thing goes for division. 12 divided by 3 is 4. Of course, you could look at it as 12 times the reciprocal, which is 12 over 3, which is 4. Same thing. Negative 12 divided by negative 3. Signs are the same. It's positive. Guess what's coming up next? That's right. Signs are different. Negative 4. Or, signs are different. Negative 4. Signs are the same. Positive. Signs are different. Negative. It's that simple, everybody. All right. So what I'm going to want you to do is do your homework packet up through page 11. If you want to save page 11, which is mixed into, never mind. Just do the whole thing. Do the whole homework packet from pages 1 through 11. Make your index cards, memorize your squares and cubes, and memorize your vocabulary. You know I'll be checking. Again, if you have any questions, thoughts, please leave a comment below. Or if you have something a little more personal, you could always give us an email at tutor@themathinstitute.com. Themathinstitute.com is our website. We're on Facebook, Instagram, YouTube, so please check us out. We love the feedback. We love that you're sitting in for these classes, and we wish you the best of luck as we continue through this introduction to higher level math.